might not be able to see much, but at least you'll hear me. Cool? All right. So we're introducing a new function, f of x equals e to the x. Now, e is an irrational constant. It's like pi. It's a non-terminating, non-repeating decimal that has special characteristics, particularly in algebra and science. All right. And our book, we're on page 667. Okay. And they introduce it with that table at the top, which honestly I've never seen before, but I'm going to write it for you. But it's not something you need to worry a ton about. Okay? F of x equals 1 plus 1 on x to the x. What they're saying is the behavior of that function is that as x, the end behavior is as x goes to positive infinity, y goes to e. So this is like the derivation of e. Okay? But honestly, I had never dealt with e in this context that I can recall. Okay? So you have to have an understanding of e, particularly for logarithms, which we're going to cover soon. But so first we just have to encounter e and see what it looks like. Okay? So I'm going to erase this now. So let's fill in the table under A using your calculator so you can get comfortable with where E is. So notice there is a button on the left-hand column. The black button says ln on it. Above it, in yellow, is e to the x. You see it? Is it in the same place for you, Nick?
Yes.
Ethan?
Where is that?
On the left-hand column, where it says ln. So on page 667, we want to complete this table. Okay? So use that e to the x key and type in the values that it's asking for. And you can round to like 3 decimal points.
So you just plug in whatever term it is?
Yep. Does everybody have that done? Okay. So now, notice below that you're graphing it, and you can see what the graph looks like by punching it into your calculator. So, and go ahead and change the window to what they have. So theirs goes from x min -2 to x max 10, and y min -2 to y max 10. You see that? -2 to 10, -2 to 10, -2 to 10, -2 to 10. So what you do is go into your y equals, use that e to the x key, and then instead of punching in a number, punch in the variable x and close parentheses. So first you're going to want to clear this. Then here you're going to go second, e to the x, x, close parentheses.
That's it? That's all I do?
Yep, that's what we're graphing. See, because isn't that e to the x?
Oh, yeah.
So in your y equals, now punch in x. You want e to the x, right?
So x min -2, x max 10?
Mm-hmm. Just like it looks like here. So, and then go ahead and look at that graph. And then we're going to plot some points, okay? So, using your table, we can plot some points. But when we do a transformation, remember what we've done lots of transformations, right? So what are we looking for when we do a transformation to start with? Like, what do we need usually? Some, like, reference points, right? I realized the way I was asking that question, you were never going to get what I was looking for. So when we're going to graph a transformation, we need some reference points to start with. So what we want to do is out of that table, as we plot, look for what our reference points are going to be. So what's one of them that's very easy?
0, 1.
0, 1. So go ahead and plot 0, 1. And plot a few more of those as well. Like 2, 7.39, 1, 2.718. And it should look about like what you've got on your calculator.
Do we connect them?
Yes. Because it's true for all the points. I mean, the function applies to all the points in between the integers. It's just that we just checked in with those, or those values that we plugged in. It's just that we checked those values that we plugged in. And then go ahead and fill in the boxes for the domain and the range of the function if you can. Or if you're having a problem thinking through the domain and range, say, I'm having a problem.
I'm having a problem.
Okay? What values of x can we plug in?
Any.
Any. So what's our domain?
X such that X is infinity.
Yeah, negative infinity to positive infinity, right? So you could say negative infinity is less than x is less than infinity. How about the range?
X is greater than or less to no.
It's the same.
Greater than or equal to 0.
Yes.
Oh, really?
Because what kind of function is this?
Exponential.
An exponential function. In an exponential function, y is never going to touch 0. Because of the way exponents work, right? If I get a negative exponent, negative, it's just putting it in the denominator. It's never, and a bigger and bigger denominator will get very close to 0, but will never be 0. So, cool. All right. So that is f of x equals e to the x. So call out for me a couple of those points. I'll put them right here. 0, 1. What was 2? 7.3.
Yeah. 6, 7.
What was 1? 2.78.
2.71.
2.71. And what's like negative 1?
0.36.
Cool. So it's about like this. Cool. So the functions on page 668. Ready? The function's y-intercept is 0, 1. Then it says another point on the graph that can be used as a reference point is 1, comma, and what goes in that box?
2.7.
Yep, and it's actually E. Put E. So that 2.73 ... is E, right? Because E to the 1 will be E. Okay. And yeah, and if you wanted to see it on your calculator, you could just once again type in e to the x 1, close parentheses. And the end behavior. Tell me about the end behavior.
As x goes to infinity, f of x goes to positive infinity.
Say that again. As x goes to infinity, f of x goes to infinity. As x goes to negative infinity, what does f of x do?
Goes to negative infinity, I guess. Well, no, it can't because it goes to 0.
It goes to 0. And then behavior. And remember, we're cataloging all this data so that we know how to do a transformation. Slide, stretch, right? And there's a horizontal asymptote where?
At 0.
Yes, at y equals 0. Okay. Now, I want to note something, okay? And I'm going to note this now so I can stop the video, okay? What was the form of an exponential growth or decay model? The form of the equation, do you remember? Okay, so if I say something increases in value by 20% every year, right? How much does it actually increase by from year 1 to year 2? Like as a decimal?
1.2.
1.2, so it's a factor of 1.2, right? Everybody follow me?
Yeah.
So what we did is we take that growth rate and we go 1 plus this, right, is our R, right? So this is used to model lots of mathematical or scientific relationships, growth and decay. So one thing that you will notice, and we'll go over this in a minute, but I'm making note on the video, is that you will sometimes have to take f of x equals a times e to the cx. So these are transformational factors, the a and the c. Okay? And change it into the form of 1 plus r to the x. You would do this by understanding what the value of e is and breaking off the 1 to figure out the actual growth rate. Okay? So like e is about 2.73, right? It would be 1 plus 1.73. And we make some moves using these transformations to understand how this is modeling some kind of growth. There's an example on page 672 using the Dow Jones Industrial Index, which we'll go over in class in a little bit. Okay. So, but there's an example on page 672 with the Dow Jones Industrial Index. All right. But first, here in class, we're going to do some transformations, which is stuff we've dealt with before: A, B, H, and K. and then we'll do the applications. Okay.